Okay, guys, welcome to Let's Get to the Marks, going through some organic A-level chemistry MCQ questions. This is just so happens to be from the OCR A-level chemistry exam board, but this is relevant and applicable whether you're doing OCR, EdXL, or AQA. So don't limit yourself. Use these to help you, provide you with practice to get really good at A-level chemistry. All right, what I suggest you do is read the question, press pause on the video, have a go now, pen and paper, or do it in your head, and then I'll go through the answers. So, question one: which compound is used as a standard for NMR chemical shift measurements? Well, the first answer is tetramethyl silane, and this is actually our correct answer, A, but I'm going to explain why. So, it has 12 hydrogen atoms, well, four identical hydrogen environments, and it's pretty much got a very low chemical shift. So every other organic compound will be to the left of it. So we use it as a standard. It's volatile, so it's easy to evaporate from the mixture. It's inert. It doesn't react with the other things in the mixture that you're running the tests on. So those are two brilliant things for it. And obviously the identical hydrogen environments, it only creates one peak. So you're going to get one large peak at 0 ppm, which should be to the right of all of the other substances you're looking at, or the compound you're looking at. Okay, of course it's non-polar, so it's great because it will dissolve in organic stuff. Now the next one, we got our deuterated, or however you say that, cheese Louise, solvent. And that's really good because that doesn't give you any peaks, because there's no difference in the number of neutrons and protons, so the nuclei is stable and you don't have rotation or spin, no nuclear spin, so you don't get a peak with that evaporates easy. So that's a good solvent for dissolving stuff in. And then you've got D2O. This is used to distinguish between the NH and the OH groups, as they kind of get the same chemical shift, which is really vague and broad. And so the best way to identify where you're dealing with an NH or an OH is to add DTO and see if it disappears. Okay, question two. Let's have a go at this one then. Which of these compounds is a secondary amide? Why don't you press pause on the video and have a go? Okay, I'm going to go through the answers. So which compound is a secondary amide? First of all, we want to ask ourselves, do we remember what an amide is? And of course, an amide has a carbonyl group and it has an amine attached, and that's what gives it the amide. So you're looking for that functional group. And you can see with A, it's not even an amide, it's an amine. And you can see with B, B's the same. So an amine is where you have an R group attached to NH. An amide is where you have the carbonyl, the C double O bond O attached directly to the nitrogen. You can see with B, the C double bond O is not directly attached to the nitrogen, so it's not even an amide, it's another amine. Now we can look at C and D, and we can see we've got this amide functional group here. You can see the amide link or the amide bond there. So we've got the amide functional group there, the C double O with the nitrogen attached. Now we just need to work out which of these is secondary and which is tertiary. So if we look at D, let's see, is this secondary or tertiary? Now, I reckon a lot of people will make a mistake and go for D. It's got two R groups attached, two CH3s, and they might go, oh, that makes it secondary. Well, actually, this is tertiary. So there's no hydrogens attached to this nitrogen, and that makes it tertiary. When you've got one hydrogen attached or one R group, that's going to make it secondary. And then when you have two hydrogens, it's primary, or when you have no R groups attached, then it's going to be primary. There is also something called a quaternary amide, and that is when you have three R groups and you're attached to the C double O bond. And those three R groups are going to make you a quaternary amide, and you're going to have that positive charge. So you're going to be like, yeah, you're going to have, when nitrogen has four bonds around it, forms a nitronium ion. So you're going to have a positive charge. Anyway, the secondary amide here is C, and you just need to get to know. All right, let's go. Let's move on. Okay, let's move. So we're on to question 3 of this MCQ pack. Which compound does not react with nucleophiles? So what is a nucleophile? Well, phile means love. What does it love? It loves the nucleus. Why don't you pause and have a go? So it's going to love positive things, a nucleophile. And if you look at the carbonyl bond, there is a delta positive carbon and a slightly negative oxygen. So the nucleophile will be attracted to that carbon. If we look at B, I'll put a question mark, stick a pin in that one for the moment. If we look here, we've got another carbonyl bond that looks like some sort of ketone, propanone there for C. So that is definitely going to be attacked by a nucleophile. And then the nucleophile is going to hunt out, remember the nucleophile as a lone pair or negative charge, it's going to hunt out that delta positive carbon for D as well. So the answer is B. And why B? Well, B, when we look at it, CH3, CH2, what kind of atom is that? That looks like prop-2-ene. So if we just scribble that down here so you can see the structure of why it's B. This is prop-2-ene. I'm not going to bother drawing all the hydrogens, can't be bothered. You can see we've got the double bond there, the electron dense region. That's going to be attacked by an electrophile. In fact, they undergo electrophilic addition normally, don't they, alkenes? So that's the alkene. So the answer is B. It won't be attacked by nucleophiles. Right, question 4. Which structure represents an alicylic compound? Don't be silly. Oh, all right, that's rubbish. All right. Anyway, which one is an alicylic compound? So we have to ask ourselves, what is alicylic? These are things like cyclopentane, cyclohexane, right? Cyclopropane. They have a ring of carbon atoms in their structure, but they do not contain a benzene ring. You might know the name for compounds that contain a benzene ring. They're known as aromatics. So they have the delocalized benzene ring, and they're known as aromatics. Alicylics are just standard cycloalkanes, basically. They have a ring, but it's just a straight carbon ring. There's no delocalized ring inside. So if we look here, this is like a kekulé or kekuli, however you say it, structure. So that's the version of benzene, the alternative version of benzene. So A, B, and D actually all contain benzene or a benzene ring. So the answer is C here, is the alicylic compound. And there we go. That's the end of the first 4 questions. Let's move on. Okay, we're on question 5. Which molecule is not planar? So what does that mean? Which molecule has not got a flat shape? So let's look at these different molecules. The first one, A, is ethene, C2H4. Now, the double bond in ethene doesn't allow rotation. There's no rotation around a carbon-carbon double bond, and therefore this is a flat molecule. It is planar. Now let's look. Let's get rid of that. Bing, bang, bosh. Don't forget to subscribe to the channel, like, share, helps me out massively, peeps. The next one is ethane, and ethane has basically got, well, each carbon has 4 bonds around it, and it's going to have a tetrahedral shape. So each of these has like a tetrahedral. So that does have a 3-dimensional shape. That is not planar. Single bonds, there is rotation around the single bond. So the answer here is B, but let me just go through the other 2, show you why not. So if we look at C, C's got a carbonyl bond, CO. Now that's planar. There's no rotation around that. That's why you get a racemic mixture, because there's equal chance of approaching from above and below with a nucleophile. And nitrile bond is the same. What is the number of peaks in the H1 NMR spectrum of this molecule? Jeez, I'm going to have to write that molecule out, guys. Why don't you pause the video, grab a pen, grab paper, see if you can work out how many H1 NMR peaks there are in this molecule. Now, this molecule has got a carboxylic acid, then it's got a CH2 group, then it's got a CH with bada bada bing, bada bong, bada bash. Oh, with an OH coming off here. And then another CH2 group. So we've got some identical hydrogen environments going on, and another carboxylic acid functional group at the other end. So we got like a hydroxydioic acid thing going on here. Okay, how many different hydrogen environments? Well, let's label them up. So we've got one here and one there. They're identical to each other. So I'm going to label them as 1, 1. And then we've got this CH2 here and the CH2 here. They're identical. That's another hydrogen environment. And what else? Got one there and another one there. So I think we're going to have 4 guys. Looks like 4. It's 3 or 4. We've got one there and we've got another OH here. And this is in a different environment than the others. So the other 2 OHs, although it does look pretty similar to those other 2 OHs, doesn't it? But it's not quite the same. So we're going to go B. The answer is 4 different hydrogen environments. Okay, let's move on. So let's go with 7, which is ethanol can be prepared by different reactions. Which reaction has the lowest atom economy? Let's zoom in. All right, so we got atom economy. What's the equation for that? It's the useful product over the total, the MR of the useful products over the total MR of the reactants. I think that's it, times 100 if you want it in a percentage, but we're going to do it as a decimal here. We don't need to do the extra step to a percentage. Which one's got the lowest atom economy, so the most inefficient atom economy? I'm actually just going to do, I know you're not supposed to, but I'm going to do the useful product over the total products. So if I add up ethanol, we got 2 times 12 for the MR of carbon, plus 5 for the hydrogen, plus 16 for the oxygen, and 1 for the hydrogen. So ethanol, I think, has an MR of 46. I'm doing this roughly, so I might make mistakes here. Now, if we times it by 2, because there is a big fat 2 in front of the ethanol, with essentially 92 of the MR of those reactants of glucose has become ethanol. And then glucose is 6 times 12 plus 12, 72, plus it's 84, plus 6 times 16, 16, plus 6, whatever it is, God, 180, let's say, for glucose. So 92 over 180, and we get 0.51. And if you wanted to do it as a percentage, go ahead, knock yourself out, but I'm not going to bother. Right, you could times by 100 if you want, 51%. This is 100%. There's only one product. It's the ethanol. It's 46 over 46. If you do ethene plus water, you get 46 MR. So it's 46 over 46. So that's one. So that's definitely not the lowest. At the moment, A is the lowest, which is 0.51. Now we've got 46 for the useful for the ethanol here, and it's over 81 for HBr. I think it's 81, 79.9 for BR and 1 for H. Oh, plus 46. What's that? 127? 46 over 127. That's going to be lower than A. So that is a lower fraction than A. So this has got the lowest atom economy so far. 46 over 127. Gosh, whack that in the calc. What's that? 0.3, whatever, 0.36. We don't have to be exact unless we get two that are very close. Now we got 46 again is the useful product is ethanol. And I could just do 46 plus I'm going to add up the carboxylic acid here. I know that's doing the useful product over the total products, but it's pretty much the same thing, right? It's the total MR. So what's the total MR here? 106? Oh, I don't know if I've done that right. I think so anyway. 46 over 106, 107, something like that. 0.43. Yeah, so it's definitely C. It wasn't close. C has the lowest atom economy. Okay, let's zing to question 8. Oh, the breakdown of ozone is catalyzed by nitrogen oxide radicals, nitrogen monoxide radicals. Which equation is a propagation step in the mechanism for this process? So we're going to have nitrogen oxide radicals. Remember, your propagation would have a free radical on either side of the reaction. They've made this difficult by not showing us the little black dot or which ones are free radicals. So they've made this a little bit more difficult. But essentially, your initiation is either going to be N2O4 splitting into NO. No, it's either going to, yeah, N2O2 splitting into, no, it's not going to be that. Be NO2 getting split by UV light into NO plus O, making that nitrogen monoxide free radical and an oxygen free radical. And now we just got to work out which one would be propagation. Well, it's either going to be B or D, me reckons. Oh, I reckon here you're going to get propagation. Get rid of that NO2. That's not the free radical. It'd be an NO free radical. So it'd be NO2. There's not supposed to be a dot there. Let me rub that out. So it'd be NO2 plus the oxygen free radical makes the nitrogen monoxide free radical plus an oxygen. So that will be a propagation step within the breakdown of O3, the ozone. Okay, which compound could have produced, let me zoom out. Which compound could have produced the IR spectrum below? We've got the transmittance on the left and the wave number underneath. So what is this? This is ethanol. So it's an alcohol. This is, what is that? Hydroxy propanitrile. And then we got ethanoic acid or carboxylic acid, basically. And then we've got an amide here. What's that? Ethanamide. So yeah, so we've got an alcohol, hydroxynitrile, a carboxylic acid, and amide. What we want to do is go to the data sheet and look up some of these peaks. Look at this really thin, sharp peak. Let's find out what that is. That's about 2,300. Actually, that's 2,250, say. It's bang in the middle of 2,200. Oh, that's periodic table. There's a data sheet. Right, let's go. Where is 2,200? Oh, it's there. It's a nitrile. Have a look, guys. I'll highlight that for you. 2,220 to 2,260. I reckon that was 2,250 on ours. And it's a nitrile. So that means it's the molecule with the CN. So we've already really got our answer because that means it's B, the hydroxynitrile. Let's just confirm that. The hydroxynitrile should have a hydroxy group there. But is that OH group there, which is around 3,000? There's two OH groups. There's one for carboxylic acids. And the one for carboxylic acids would be broad and is like 3,000 to 3,300. This is a little bit further on. The wave number's a little bit larger. This is the wave number of an actual OH group on an alcohol, which is roughly 3,200, 3,300 to 3,600. So the peak for this OH group, which you find after 3,000, is too far over to be the carboxylic acid one. Look, I'm going to show you. Look at the alcohol one. It's 3,200 to 3,600. Whereas if it was a carboxylic acid, it wouldn't get as far as it wouldn't go past 3,300. So yeah, it's B. Right, 10. Benzene reacts with an organic reagent in the presence of a halogen carrier to form phenyl ethanone. Okay, what is the organic reagent required? So I need to add a carbonyl group there on to benzene. Well, the top one it can't be because there's no C-double-O bond. There's a C-double-O bond in both B and C. Now, C is an acyl chloride, like ethanoyl chloride. And if you remember, you react that with a halogen carrier and it removes the chlorine to form AlCl4 with a minus charge. And you get left with this really powerful nucleophile, which is great for adding sort of aldehyde groups or ketone groups onto a benzene ring. And there we go. That kind of then attacks the ring. You get that horseshoe form. Da-da-da-da-da-da-da. So the answer is C. And you just got to learn that. How many straight trains? I can't speak. Rewind. How many straight chain structural isomers of C7H15Cl contain a chiral carbon atom? Why don't you pause the video, write them out with a pen and paper, have a go. Okay, I'm going to do it here. So 7 carbons, that's heptane. So we've got chloroheptane, but is it 2 chloroheptane, 1 chloroheptane, 3 chloroheptane, 4 chloroheptane? You get the idea, right? So here's my skeleton for heptane, straight chain. A chiral carbon, what do we need to know about chiral carbon? A chiral carbon is a carbon with 4 different groups attached. So a chiral carbon has 4 different groups. Look at this first one. This would be 1 chloroheptane or just chloroheptane. And it's got 2 hydrogens attached to that first carbon. You see those 2 green H's? That means it cannot be a chiral. Let's move the chlorine atom 1 along to form 2 chloroheptane. Now it's got a methyl group on that carbon, a hydrogen atom, and a pentyl group, right? So we've got methyl, hydrogen, pentyl, chlorine, 4 different groups. So 2 chloroheptane is one of our ones that has a chiral carbon. Let's look at 3 chloroheptane. That's got an ethyl, hydrogen, butyl. So we've got an ethyl here, a butyl there, a hydrogen there, and a chlorine at the bottom there, and that means that is a chiral carbon. So we've got 2 different isomers so far. Let's move it 1 more across to make 4 chloroheptane. Is this chiral? No, it's got 2 propyl groups on either side, a hydrogen and a chlorine, so it's only got 3 different groups attached. So that means that the total amount of isomers I can form with a straight chain is 2. You might say, but sir, you haven't done 5 chloro. There is no 5 chloro. Remember, if I move my chlorine atom there or there, or there or there, this is a symmetrical, so it's going to be, that's 2 chloroheptane and 3 chloro, and this is 2 and 3. So there's only those 2 options will have chirals. The 2 and 3 chloroheptane is the one. 2 chloroheptane or 3 chloroheptane, they're going to have the chiral carbons if you keep the chain straight and you don't start putting methyl groups on. So the answer is B. Okay, let's move on to question 12. Question 12. The mass zooming out, the mass spectrum of CH3 CH2OH is shown below. Which ion is responsible for the peak with the greatest relative intensity? We can see it's about 98% or something relative intensity. And that line is at 43. That big tall line is at 43, the MR. So we just need to make sure that which ones of these have an MR of 43? Well, if I add CH2OH up, it is possible that you would get that fragment because it could snap off there. So it's possible, but when we add this up, this has an MR of 44, so it can't be A. So which one could be responsible for the 43 relative intensity, the biggest relative intensity at 43 MR? Add this up, 15 plus 14 is 29, plus 11 is whatever that is. Yeah, plus 13, sorry, is 42. So it can't be B. So now if I add both of these up, both of these are going to come to 43, I believe. I probably haven't done this right because my brain's not very good at maths. So I think they're 43 each, C and D. Now, if we look at this bottom one, D, it can't form CH3CO. There's no CH3 group attached to the CO there. So there's no CH3 attached to a CO bond, so it can't be that. There's a CH2 attached to an O, but not there. So yeah, it's not going to be that. There's no CH3CO, so it can't be that one. D is an impossible fragment, C is a possible fragment, and it has the right MR to be the one with the highest intensity. Right, question 13, just 3 more to go, folks. Which statement supports the delocalized model for the structure of benzene? All carbon-carbon bonds have the same length. The enthalpy change of hydrogenation of benzene is less exothermic than expected. Bromine reacts with benzene less readily than with cyclohexene. This is a good one to test you on your evidence for the delocalized ring structure of benzene rather than the Kekule structure or Kekule structure. Well, if it was the Kekule structure alternating single and double bonds, benzene would not have equal bond lengths. So yes, having equal carbon-carbon bond lengths is evidence for the structure of benzene. I can't remember, they're like 143 and the double bonds like 133 and the single bonds like 154. So the benzene bond length is an in-between length, in between a carbon-carbon single and carbon-carbon double. So yes, it's evidence for benzene. The enthalpy of hydrogenation is less exothermic. Benzene is more stable. It doesn't release as much energy when you hydrogenate it. And benzene reacts less readily with cyclohexene. Yeah, benzene's less reactive. Remember, cyclohexene is going to do electrophilic addition, whereas benzene is going to do electrophilic substitution because it's much harder to add to the ring and break the ring. It wants to maintain the ring. So yes, all 3 are evidence for the existence of the benzene structure with the delocalized ring. Right, question 14. A solid organic compound can be purified by recrystallization. Which statements about recrystallization are true? The organic compound is more soluble in a hot solvent. Yeah, that's going to be true. Anything's going to dissolve better in hot things. It increases the solubility of solvents. Hot solution is cooled. Yes, before you're going to cool it so the product actually solidifies and crystallizes out. The melting point of the purified organic compound is lower than the impure. This is true. Impure compounds have lower melting points than pure compounds. It's why we add salt to ice in the winter. We make it impure the water and we lower its melting point by making it a mixture, by making it impure. So yes, and they also have a wider range. They melt over a range rather than an exact temperature. Right, B. We're on to the last one, folks. We're nearly done. Question 15. Which of the following could react with the compound below to form a carbon-carbon bond? Don't forget to pause the video at the start of all of these and have a go in your head. So which of these reagents is going to form a CC bond when it reacts with this molecule? So let's see, we've got CH3Cl and AlCl3. I think this is going to, AlCl is going to act as a halogen carrier, and they're going to form AlCl4 with a minus charge and CH3 plus. Now that CH3 plus is a nucleophile, and that nucleophile is going to attack the benzene ring, right? And essentially a pair of electrons are going to be donated temporarily from the benzene ring like so. We draw an arrow from the ring going out, and then it's going to form that horseshoe, and the CH3 is going to join on where there's a hydrogen, and eventually the hydrogen is going to break itself off and donate its electrons to reform the ring, and you're going to be left with a carbon-carbon bond. Let me just zoom in and show you that. So you're going to get left with a carbon-carbon bond because you're like methylating the ring or whatever. So you're adding a methyl group there, and it's going to attach to that carbon there. So you are forming a carbon-carbon bond when you do that. Right, so 1 is true. That will form a carbon-carbon bond. Now we've got KCN. You can use HCN, but hydrogen cyanide is a little bit dangerous. I mean, KCN is pretty bad. The lone pair here on the CN, the nitrile, is going to attack that carbon, and we're going to get the bromine breaking off, aren't we? And we're going to end up with a CC bond where the nitrile attaches to that carbon, the delta positive carbon there. And then let's look at the alcohol and sulfuric acid, and we've got a carboxylic acid. You know, this is going to be an ester. Alcohol and carboxylic acid make ester, so that H is going to break off. We're going to get the CH3 there, water molecule released, condensation reaction. We're going to get the ester form, but there's no CC bond formed there, so the answer is B. It's just 1 and 2. The third one forms the ester. Don't forget sharing is caring. Hit the like, punch up the bell, subscribe. I'll catch you lot on the next vid.
You're still here? It's over.
Okay, welcome to Let's Get to the Marks. Going through a little question here, organic chemistry for A-level. Let's go. Why don't you pause the video and have a go? What is the systematic name of alcohol A, and what is the structural formula of alcohol A? Grab pen, grab paper, pause the video, have a go at this one, and then I'll go through the answer. All right, I'm going to go through the explanation. I have a cold, so you may have to forgive me sounding like a donut. Right, the main chain looks like it's got 4 carbons, but do we think that methyl group is 2 or the hydroxy is 2? Well, hydroxy, the OH group, takes preference over the methyl, so it's going to be 2 for the hydroxy and 3 for the methyl. The main chain is 4 carbons long, so we're looking at butane, not propan. So we're looking at 3 mether, 2 or 3 mether butane 2. I was going to say 3 methyl 2 hydroxy, but we're looking at 3 methyl butane 2O. Okay, now what is the structural formula of alcohol A? These ones can be tricky actually. How do you write this out as a structural formula? Well, I like to make it into displayed first, and then you can see the different groups you're dealing with. So with the structural formula, you're trying to actually describe the order of the atoms that are attached to each carbon. So we want to start with the main chain. We've got CH3, okay, and I'm circling that here, but we've got 2 CH3s. So we can actually bracket that because they're coming off of that next carbon, and we can put a little 2 next to them. So CH3 2. Then we have a CH here. So we're going to go CH3 2. They're attached to the CH. Then we have another CH, but this CH is attached to an OH. Now you don't have to, but if you like, you can bracket the OH just to make the functional group stand out. And then it finishes with a CH3, and that's going to get us a mark. Lovely jubbly. Okay. Ba, 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 ba. The chemist heats alcohol A with an acid catalyst to form a mixture containing 2 alkenes. Draw the structures of the 2 alkenes formed in this reaction. So we're going to zing back up, and then what I want you to do is sketch it out on paper, have a go at turning it into the 2 different possible alkenes that can be formed. So you can turn alcohols, you can dehydrate them into alkenes using sulfuric acid. So this is a dehydration. We're going to form an alkene. What are the 2 possible alkenes that can be formed? Why don't you pause the video with your pen and paper, see if you can sketch out the 2 alkenes that will be formed. Now, it's going to lose a hydroxide and a hydrogen atom. And the clue is that you need to have a carbon adjacent to the carbon with the OH. So here's the carbon with the OH. Now you can see I'm drawing 2 other carbons. They're the adjacent carbons. They are going to donate their hydrogen. We're going to get a water molecule coming off because the OH plus one of these hydrogens. So either of these hydrogens can donate their electrons. Sorry, I had to say donate their hydrogen, but they can donate their electrons to the bond. So the double bond will form on either side of the carbon with the OH attached. Okie dokie. So there we go. We have, here are your 2 possible ones. So you're going to get 2 marks if you drew those. So you just put the double bond either side of where the OH used to be. The OH obviously comes off with one of those hydrogens when it forms water. So like that. All right, let's zing down and do the next question. Once again, I apologize for my disgusting cold, which, yeah, makes me sound like a right wally. Okay, the chemist heats alcohol A with sodium chloride and sulfuric acid. Construct a balanced equation for this reaction. Show the structures for the organic compounds in your equation. All right, what I recommend is you grab your paper, grab your scrappy old paper and your pen, and you have a go at writing the balanced equation for this reaction. You need to do either displayed or skeletal formula for the organic compound. So for alcohol A, we need to actually show it in either displayed or skeletal. So I'm doing skeletal. Now we're going to add it to sodium chloride, and we need some H2SO4, some hydrochloric acid. And now I need to actually show the organic compound formed. Of course, there's one inorganic compound formed as well. And what we're going to do here, folks, is we got some nucleophilic substitution going on. So you've got your delta positive carbon there, and you're going to have your chloride ion attack that, and your water molecule is basically going to break off, and you're going to lose one of the hydrogens from the sulfuric acid. So what you're going to get forming is, oh, blimey, 3 mether 2 chlora, whatever that is, butane, and you're going to have a water molecule and sodium hydrogen sulfate forming. All right. Okay, compound B, shown below, is refluxed with excess acidified potassium dichromate to form a single compound. Complete the equation for this reaction. So once again, what you're doing here, grab your paper, grab your pen, you're going to pause the video and have a go. What is compound B going to what is compound B going to become if we completely oxidize all of the OH groups to their maximum because we're refluxing? So let's look at the first OH group. The first OH group is a primary alcohol. How do I know that? The carbon atom next to it has two hydrogens attached. So it's a primary alcohol. This means it can be refluxed first to an aldehyde and then to a carboxylic acid. If you leave it under reflux and heat vigorously with the oxidizing agent, it will go to a carboxylic acid. Of course, our oxidizing agent will go green to orange. We don't need to know about that here. So I'm going to redraw this compound, but I'm going to turn the final carbon into a carboxylic acid. Now, if you add up the total amount of oxygens on compound B and my new total amount of oxygens on the right, you can see there are 4 oxygens. There are 3 oxygens in total on compound B and 4 oxygens on the right on our new compound. But also worth noting, when we form that carboxylic acid, I've circled the 2 hydrogens on compound B that were lost. So we actually lost 2 hydrogens. So I've written the 2H over there. So we gained an oxygen and 2 hydrogens have been lost. Now we look at the second OH group. It's a secondary alcohol and it's oxidized to a ketone. So I'm just going to put the double bond O here. Remember, secondary alcohols get oxidized to a ketone. I've got 5 bonds now. I need to remove that hydrogen. So not only did it didn't gain an oxygen, but it lost 2 hydrogens. Look, I'll circle them on compound B. It lost the one there from the OH group, and it lost another. So in total, we removed 4 hydrogens, which means what's going to happen to those hydrogen? They're not going to come off as hydrogen gas. They're going to form water because we've got oxidizing agents knocking about. So they have the ability to form water. Now, those 4 hydrogens are going to require 2 oxygens to make the water, and we added an oxygen when making the carboxylic acid, didn't we? Because we went from 3 to 4 oxygens. So how many oxygens in total? 1 to convert compound B to the carboxylic acid by adding an oxygen, and then we needed 2 more oxygens to form the 4 water molecules with the 4 hydrogens we removed. That leaves us with a total of 3 oxygens needed. And so we just put 3 next to the O in brackets and we turn the water to 2H2O. So 2 of the oxygen atoms that we needed to be added were used to form the 2 water molecules and an extra oxygen to form the carboxylic acid where we added an overall oxygen to the compound. Okay, there we go. Wunderbar. That's the end of that one. And that's worth 2 beautiful marks. Don't forget, guys, these videos take me a while to record and film. All right, I'm not filming them. You know what I'm saying? Well, maybe you don't. I'm waffling. But essentially, do me a favor, hit the like. Helps me make more of these A-level chemistry questions for you guys. Okay, let's zing on. The flowchart below shows some reactions of compound C. In the boxes, draw the organic products of these reactions. What I need to do is zoom out. And there we go. We've got compound C, so it's like a dioic acid, but we got the double bond in the middle. So we've got an alkene and we've got 2 carboxylic acids. First of all, what happens when you use alcohol with an acid catalyst? So you're going to turn those carboxylic acids into esters. You're going to do a condensation reaction. We're going to remove some water and form an ester. So we just need to draw what that's going to look like. And we can put the double bond back, but we're just going to form an ester. And that is methanol. So we're going to make methyl esters. We're going to form 2 methyl esters at the end of each side of this molecule. Oh gosh, I couldn't fit that in the box. Let me redraw it again. There we go. So we've got the carbonyl group. And we got the methyl ester there. Let's go to the other side. Carbonyl, oxygen, ester linkage, and methyl ester. Obviously, we're going to lose 2 water molecules here in the formation of those 2 esters. And we're going to put the double bond back there. Roughly. That is one ugly drawing. Yeah, that methyl group, I don't know what that looks like, but I did get a D in GCSE art. So we've got some sort of diester there. Right, now we're going to do steam and phosphoric acid. Now, this is a hydration reaction.
And what we're going to do here, we're going to hydrate this alkene. So we're just going to replace the carboxylic acids. They're going to stay as is. But the phosphoric acid with steam, you're adding H2O. And you're just going to add an alcohol group anywhere along here. Okay, so we add one hydrogen to one side, and the double bond disappears. And we add OH from the rest of the water molecule to the other side. So we get an alcohol. Now we're going to do polymerization. When you do addition polymerization, you just want to you want to tuck the functional groups up here, and you just want to concentrate on that double bond where the CC double bond is. Turn that into just a single bond, add brackets to either side of it, and tuck everything else up on the other sides, and that's your repeat polymer. Booyah! All done. Okay, welcome to Let's Get to the Marks. I'm going through an A-level chemistry walkthrough question on amino acids. So let's get into it. The general formula of an alpha amino acid is RCHNH2COOH. The alpha amino acid cysteine has an R group CH2SH. Shows optical isomerism. Draw 3D diagrams to show the optical isomers of cysteine. It's worth 2 fat marks. Why don't you grab a pen, grab some paper, press pause on the video, have a go, then unpause and watch my explanation. All right, I'm going to go through the answers now. So what you can see here is they've given us a nice reminder of the general formula of an amino acid, an alpha amino acid. So remember, you've got your carbon atom in the middle, your carboxylic acid group. You can draw that to the right or left. It doesn't really matter. You've got your NH2, your amine or amino group on one of the sides, and then you've got your R group. Now, some teachers like to put it at the top, and some teachers like to tell you to, or lecturers, college tutors, whatever, like to tell you to put it at the bottom. It really doesn't matter where your R group goes, and then your standard hydrogen coming off that carbon. Now, what is an optical isomer? Hopefully you remember an optical isomer. Some people get these mixed up with EZ isomers, but optical isomers are ones that need a chiral carbon. And if you have 4 different groups attached to a carbon atom, and so there's one amino acid where you won't get this, where the R group is a hydrogen, you don't get that. But with all other amino acids, you're going to get chirality and therefore optical isomers. Now we're going to draw these 2 optical isomers, so let's get into it. Now, what a lot of people get confused with is this is going to be a tetrahedral structure. Why is this a tetrahedral structure? Well, carbon is a group 4 element. It has 4 electrons surrounding the central atom. If it is bonded to 4 other things, then it has 4 electrons from those bonds. So it has 8 electrons altogether around the carbon atom. And therefore, 8 divided by 2, it has 4 electron pairs, and none of them are lone pairs. So it forms the tetrahedral structure. Now, what confuses some people is, what groups do you draw where? It doesn't matter. This structure has 109.5 degree bond angles between all the 4 different bonds coming off the carbon. So it doesn't really matter. You could rotate this in any direction. It doesn't matter which way or where you put the 4 different groups. Now, you should always do a wedge coming out the paper, and like this triangle with bold black. You can do a wedge, which is quite hard with the lines. I tried to do it for the carboxylic acid group. Again, it doesn't matter which one has the wedge. It doesn't matter which one has the dashed line. You must do a dashed line or a dashed wedge. And it doesn't matter which of these 4 groups. 2 of them need to have a dashed line, or one of them a dashed line and one of them a solid black wedge. Now that's going to get me a mark. So any drawing you do here, as long as you have a dashed line and a solid wedge, will get you a mark. I've chosen to put the R group at the top, but it could have been any other group at the top. It could have been a hydrogen atom at the top and the other 3 groups coming off underneath. Think of it as like a pyramid with another bond coming straight out the top of the pyramid, the apex of the pyramid, and that's your tetrahedral structure. Now, all I need to do is swap any 2 of these groups around, redraw the structure and swap any 2 groups around. So I'm going to redraw it with the CH2SH in the same place up and above, and I'm going to swap around the carboxylic acid to the other side, and I'm going to swap that with the NH2. So it's obviously, I'm not going to write H2N, I'm going to write NH2 here, the amino group. Now the hydrogen is there. Now a lot of people, it's their spatial awareness, and don't blame you, it's quite difficult. A lot of people will say, there's no difference, mate. You've drawn the same thing. If I rotate the right hand one, surely I can make the left hand one. How are these mirror images that are non-superimposable? If you put these over each other, you can't rotate these and get these to a match. And so you can't rotate these. And you might think, yes, I can rotate them round. No, look, let's look at the right-hand one and imagine we could turn this right-hand one. I'm going to draw an arrow. Let's imagine we could turn this right-hand one around like this. Look at this green arrow. If we could rotate it anti-clockwise, if you did that, the carboxylic acid group would end up where I've circled the green H on the left-hand one. It would rotate to there, the carboxylic acid group, and the H would be before it. Okay, so you can't actually rotate these and get them to be in the same position. They are non-superimposable, hence the word chiral, like your hand. You can't put your right and left hand over each other. Anyway, let's get to the next question. The alpha amino acid lysine R equals CH2 4 NH2 reacts with an excess of dilute hydrochloric acid to form a salt. Draw the structure of the salt formed in this reaction. Why don't you grab your pen, grab your paper, pause the video, and have a go? All right, I'm going to go through the explanation. So what I want to do, start off by just drawing the general formula for an amino acid, right? So same thing again. We've been told what the R group is. It's a slightly different one. And boy, have I not given myself room, because that is CH2 for NH2. Now, to be fair, I could just write CH2 and put a 4 next to it in the brackets, but I'm a bit of an idiot and I'm going to draw the displayed formula of all the CH2s out for you, just so you can get the full feel of it. And I've run out of room, so let's select that, drag that, rotate, move that down, and get it in the right position. This is going to be a pain. All right, what if I put it there? No, I've got to do another 2. So why didn't I just write CH2 brackets for? This is why you should just, oh, don't. All right, let's move it over there. Now I've got enough room. Right, NH2, bada bada bing, bada bada bong. Right, we've got an excess of dilute hydrochloric acid. So think about this. Hydrochloric acid, going to dissociate. You're going to have chloride ions. We're going to form a salt. But what is an acid? An acid is a hydrogen donator. What can accept a hydrogen here? Well, you've got an amino group which has a lone pair on the nitrogen. Remember, nitrogen's in group 5. It's got 3 bonds, so it's got a lone pair. It can accept a hydrogen, and then you get this little positive charge forming on each of those NH2s, which have now become NH3s. Although I've said NH3s, they are not ammonias, they are nitronium groups, because there are 4 bonds, like in ammonia, NH4+. And so why a salt? Because we're going to get an ionic interaction with this covalent molecule. We're going to get chloride ions, which are negatively charged, attracted to those, and that is going to get you the 2 marks. You want 2 chloride ions, 2 plus charges on the nitrogen, and 3 hydrogens on each nitrogen. Boom! Alrighty then, we're on to the last bit of this A-level chem question. Is worth 3 marks. C. Alpha amino acids can react to form proteins. A short section of a protein chain is shown below. A student hydrolyzes the protein with hot sodium hydroxide aqueous solution. Draw the structures of the organic products formed from this section of the protein. So what's that? Sodium hydroxide's a base, right? It contains hydroxide ions, fully dissociates. It's a strong base. So we've got loads of hydroxide ions about. But before we get to that, how are we going to know where to break this into 2 amino acids? Identify the peptide link. Now, the peptide link is that amide link, if you're a chemist, which we are. So that's where we have the NH and the C double bond O, which I've circled in green. That's the peptide link. That's where we're going to hydrolyze. So break that bond there. Let's redraw the 2 amino acids and then see what we can do. Okay, so let's get on with that. Okay, so yeah, you should pause the video and have a go at this on paper. This one's a tricky one, so if you can get all 3 marks, you've done frighteningly well. So what I'm going to start by doing is redrawing this, but I'm going to turn it back into an amino acid first, and then we'll work out what's changed with the amino acids, because obviously if you're doing acidic hydrolysis or alkaline hydrolysis, this is alkaline, you're going to get a bit of a difference. So this is my first marks. I've reformed the first amino acid. Of course, hydrolysis, I'm going to add an OH back to the carboxylic, the carbonyl group. So you see I've made a carboxylic acid again. And what we're going to do now, I could leave the H on the left hand side as a dotted line, but I'm not going to. Now, because we've got sodium ions knocking about, not even the sodium ions, we've got the hydroxide ions knocking about. This is alkaline. The hydrogens are going to be removed, leaving those as negatively charged. Now let's draw the other one. Remember, we're in sodium hydroxide is a proton acceptor. Well, really, the hydroxide ions, the sodium isn't a proton acceptor, but the hydroxide ions are. Let's draw out the second one. I will recheck this as well, because I could have made a mistake. So I just want to start with the redrawing it out and adding back in any OHs, but then removing any H's where we've got some hydrolysis taking place. So what I want to do here, we've got these hydroxide ions. What are they going to do? Well, they're going to remove that hydrogen. Look, that pink hydroxide ion, react with that hydrogen. And what about down there? No, that's a carbonyl, like ketone type amide link. That's not going to be affected. But this is going to become O minus. What else might change? Aha, hold on a minute. I made a mistake on the first one. Have a look here. We got the alcohol OH. Hold on a minute. Carboxylic acids are acids. They will donate their protons in alkaline conditions. We all get that, right? The hydrogen from the carboxylic acid is given to the hydroxide. But the alcohol is not really a strong acid, even a weak acid. It's not a very good acid. It's not going to donate its H. So I shouldn't have removed that first H. So I get the mark for the first one now. Now we're looking at the second one. Now, under very harsh, hot, because it's hot, sodium hydroxide conditions, what can actually happen is a process called deamination. And with deamination, you can lose, in certain situations, we can lose from the amide part where the linkage is, we can lose the NH2. And we want that off of where we have an amide link. So you can see here, I've got an amide link with the C double to the O and the NH2, that NH2 can be deaminated. Notice the other NH2s are not deaminated. They are not the amide links, but the NH2 in the amide link can be removed to form ammonia, and it would release ammonia as a gas. Okay, and then hydroxide would add on, and then the H would be stripped by another hydroxide ion. And if you want, you can add the sodium pluses in where the minuses are, but you don't have to. Now, the ammonia will come off there and join with the hydrogen, but to form ammonia is deamination. You don't have to put the sodiums in, but you can do if you want. And that's going to get you all of the marks. Put any questions you've got. Don't forget, sharing is caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. I'll catch you lot on the next video.
You still here? It's over.
Welcome to Let's Get to the Marks. Going through an A-level chemistry question on phenols and aromatic compounds. Let's go. This question is about aromatic compounds. Phenol undergoes nitration more readily than benzene. A student carries out the nitration of phenol with dilute nitric acid to produce 2-nitrophenol and 4-nitrophenol. A small amount of 3-nitrophenol is also produced, and here we have the three structures. The student thought that C13 NMR spectroscopy could be used to distinguish between these 3 nitrophenols. Explain whether the student is correct. It's worth 3 marks. Why don't you pause the video, have a go. All right, I'm going to go through the explanation. You should have a go at this on paper first, see if you can get the 3 marks. So if we look at this first one, you can see there's 6 individual carbon environments. Look at this second one now. You might think that this is the same as this, but just look at the positions. They're all unique. So when we look here, we have 4 different positions. Now, you might think that 4 and 2 are the same. And then we've got a 5th position here that's unique. Look at 4 and 2. We might think, oh, they've got a nitrate in the middle. They're the same. But look, 2 has a hydroxy group to its right and 4 doesn't. So they're unique environments. You have to check them very carefully. These are all going to be unique. We're going to have 6 again. Now look at 6 and 2. You might think, well, they've both got a hydroxy next to them, but 6 is 2 sections away from a nitrate, whereas 2 is only 1 from that nitro NO2 group. Okay, anyway, enough of that. Both the first 2 have 6 carbon environments. You cannot distinguish between 2-nitrophenol and 3-nitrophenol using C13 NMR spectroscopy. So we could say that the student is wrong. However, they won't give you a mark whether you say they're wrong or right, because they are right and they are wrong, as we shall see. But we're going to say no, the student is not correct, as you cannot distinguish 2-nitrophenol and 3-nitrophenol. Both have 6 carbon environments, so cannot be distinguished between each other. Okay. Now let's look at the next one, which is 4-nitrophenol, and it's got a hydroxy group on the first carbon here, and then these 2 are identical because they're the same distance from the NO2 and the same distance from the OH. And then this one is the 3rd environment, same distance from the OH and same distance from the NO2, so they're identical. And so there's actually only 4 environments on this one. So we could say the student's kind of correct, because you can distinguish 4-nitrophenol from 3 and 2. So 4-nitrophenol can be distinguished from 3-nitro and 2-nitrophenol, as it only has 4 carbon environments compared to 6 with the other 2. So the student is wrong. You couldn't distinguish them all, but you can distinguish between 4 and 2 and 3. And there we go. That's going to get you to 3 marks, guys.
And don't forget to take the time to hit the like on the video if you're finding this useful and helping you with your A-level chemistry. It encourages me to make more videos. And don't forget to leave a message in the comments if you can think of any way to improve my videos, or you've got any suggestions or any specific questions you want me to go through. All right, we're going to move on to the next part of this question. So we're looking at Part 2. Explain why phenol is nitrated more readily than benzene. Grab your pen, paper, pause the video, have a go. It's worth 3 marks. Try and make 3 points. All right, I'm going to go through the answers now. So yeah, unpause and watch this. Here we go. Okay, so this is our phenol. Phenol is a benzene ring with a hydroxy group attached to the ring. Now, it donates its the cloud of electrons on the oxygen. Remember, there's 2 lone pairs on the oxygen. They are going to be delocalized into the ring, or partially delocalized into the ring. The cloud overlaps with the pi ring, extending the pi ring and making it more electron dense. So we can say, in the proper technical language, the lone pair on the oxygen is partially delocalized into the pi ring. Get you a mark. This makes the benzene ring more electron dense or more electron rich, meaning there is a higher volume or density of negative charge in that area. And that means it's more attractive to electrophiles, things with a positive charge. It's more susceptible to electrophiles that can accept electrons. And that's going to get you the 3 marks. Right, final part of this question. Methylbenzene reacts with sulfur trioxide to form D, shown below. The electrophile in this reaction is SO3. Complete the mechanism for the formation of D, show curly arrows, and the structure of the intermediate. So here we've got methylbenzene, here we've got the SO3, you can see it here, I've circled them. And we need to show the intermediate, we need to show curly arrows on the reactant, curly arrows on the intermediate, correctly drawn, and that's going to get us 3 bad boy marks. All right, let's get into it. Let's zoom in a little so we can get down to this and you can see exactly what we've got to do. Why don't you pause the video, have a go on scrap paper, let's go. So as you can see from the final product, we're substituting onto the ring, and these follow all the patterns of substitution. So do you draw the arrow from the electrophile to the ring? No. Electrons move, protons don't move. Don't make this mistake and draw the curly arrow trying to get over that double bond to the delta positive sign, because that kind of shows it would be repelled by a double bond, and that's incorrect. Don't draw the curly arrow from the center of the benzene ring. Draw it from the edge where the line of the benzene ring is. So you're showing the electrons are moving. The arrowhead means there are 2 electrons moving. It's a pair of electrons, and they're moving to the sulfur atom. So you need to identify that. Make sure the arrow doesn't point to a bond, which would repel electrons. So we then need to break the oxygen bond. Why? Because you can see there's an O- on the final product. So one of those bonds has broken, and of course sulfur's in group 6. It can't have 7 bonds, so one has to break. So we're going to draw our methylbenzene, but this time we're going to do the horseshoe upside down. Don't go past the points. Don't make that horseshoe too big. Don't go past those points. Put the plus sign in the horseshoe to show the benzene ring is, the pi ring is temporarily broken. Here is our SO3 group attached with the O-, and we temporarily got the situation where we have hydrogen and the SO3, but the hydrogen then donates its pair of electrons from its covalent bond to the positive sign there and reforms that delocalized ring, which we can see in the final product, and you can see the hydrogen ion has come off. And you just follow in the rules and to what you know with the substitution onto the benzene ring. And there we go, 3 marks. Boom! Going through a question about the hydrolysis of haloalkanes. This is an A-level chemistry question. So read the question, pause the video and have a go, and then I'll go through the explanation. So the rate of hydrolysis of a haloalkane depends on the halogen present. State and explain the halogen in the haloalkane and how it affects the rate of hydrolysis. Chlorocyclohexane is hydrolyzed with aqueous sodium hydroxide. Outline the mechanism for this reaction. Show curly arrows, relevant dipoles, and the products. Why don't you press pause, have a go with some paper and a pencil. Make your revision active. Okay, I'm going to go through it. So you can see that the haloalkane have carbon halide bonds, and they are polar. So we have a delta positive and delta negative halide with a delta positive carbon. The water molecule, or a hydroxide ion, is going to attack that. So there's got a little bit of nucleophilic substitution going on here. Now, what's going to control the rate of hydrolysis? Some people get mixed up and think, well, fluorine's the most electronegative, so it's going to attract the nucleophile more, but it actually, that is outweighed by the mean bond enthalpy. And carbon and fluorine, the mean bond enthalpy is way higher than carbon and chlorine, and then carbon and iodine. So, yeah, the rate of hydrolysis of haloalkane depends on the mean bond enthalpy, and that's going to get you a mark. Now you need to explain the pattern. So the CF bond has the highest mean bond enthalpy. What does that mean in terms of hydrolysis? It means more energy is needed to break the CF bond, which means the reaction is going to happen more slowly. So the CF bond has the highest mean bond enthalpy, so the rate of hydrolysis is slowest. Whereas with the CI bond, it has the lowest mean bond enthalpy. It's the easiest to break, requires the least energy to break. So your haloalkane containing iodine is going to have the highest rate of hydrolysis because the CI bond is easier to break. And if you want, you can point out the order and say it goes CF, CL, CBr, and then CI. I missed out CBr on my little picture here on the right hand side, but it don't really matter about talking about all of them as long as you've got that pattern and you've explained the link between mean bond enthalpy and the rate of hydrolysis, and the link between the type of halide and the mean bond enthalpy. So they're the two marks you're picking up there. Bish bash. Right, now we're going on with chlorocyclohexane is hydrolyzed with aqueous sodium hydroxide, NaOH with an AQ in brackets. Outline the mechanism for this reaction. Obviously, the sodium ions are going to be spectator. Well, they might react with the chlorine afterwards to form sodium chloride. But we've got these hydroxide ions. These are going to be our nucleophile. They're attracted to the positive part. What's positive? Well, it's going to be the delta positive carbon atom. I'm going to get rid of that C because this is a skeletal formula and we don't want to mess about with that. I will show the dipole. So we've got the delta positive there. The lone pair is attracted there from the nucleophile. We know that chlorine's in group 7. If you're in group 7, you can only have one bond, so always check the group. So it has to break in order to allow the hydroxide ion on. It cannot stay there as well. It can't have... yeah, chlorine's got to break off, so that carbon can't have that many bonds. Okay, so what we're going to do is our chloride ion is now got a lone pair and is negative and hanging about, so that's going to be part of our product. So we've got the two curly arrows, we've shown the dipole, so that gives us 2 marks, and then we've shown the 2 products, the alcohol and the nucleophile. Awesome. All right, enough of my whiffle waffle waffle. Let's move on. A student hydrolyzes a haloalkane E using the following method. 0.01 mole of haloalkane E is refluxed with excess NaOHAQ to form a reaction mixture containing an organic product F. The reaction mixture is neutralized with dilute nitric acid. Excess silver nitrate aqueous is added to the reaction mixture. We get 1.88 grams of a precipitate G that's formed. The organic product F has a molar mass, that's Mr, of 74 and has a chiral carbon atom. Draw a label diagram to show how the student can carry out the hydrolysis of haloalkane E. Pause the video, have a go. Okay, you should see that I have circled in pink reflux. So it told us it's reflux. You have a choice. They allow you to use a round bottom flask or a pear-shaped flask. I'm using the pear-shaped flask because it's nice. It looks like a heart. Woo! And you can write heat, or you can draw a heat source like a water bath or a Bunsen burner. I mean, you wouldn't really want to use a Bunsen burner with organic solvents because they're flammable. And then we need to draw a condenser squeezed into that pear-shaped flask. My God, I got a level 4 in GCSE art, so you can see that by my crusty ceiling. Make sure the pear-shaped flask or your round bottom flask is fastened and sealed tight to the condenser. The end of the condenser should be left open to allow excess gas to escape and relieve the pressure. You don't want some sort of explosion. Now, into your condenser, you need to show the water in and water out. Just memorize this. Water in is always lower down gravity-wise. So, and that is to ensure that it completely fills with water and we get the maximum heat transfer. If it was to come in the other way, look, the top part wouldn't get filled with water if I had water in the other way. Okay, so I'm going to label this up, pear-shaped flask. You can use the round bottom flask. I've drawn it on the left over there. I'll label it over there for you if you really like. And then you might want to put some anti-bumping granules in there as you're going to be heating pretty violently under reflux. Yeah, this is a Liebig condenser, but you can just call it condenser. You don't need to say Liebig. And then the top of the flask is open. That's going to relieve pressure from excess gas and stuff like that. You don't want to seal that during reflux. Okay. But it must be sealed here because we don't want gases to escape. at the point where the condenser and the pear-shaped flask or round bottom flask are joined. That must be sealed. And that's going to get you the 2 marks. Now comes the hard bit to this question. Analyze the information to identify E, F, and G. It's worth 3 marks. Bear with me because this bit's a little bit tricky. Why don't you pause the video, read this information, see if you can work out what E, F, and G are, work out their structures, have a go. And yeah, pause the video and have a go on some scrap paper. I think this was a particularly hard question, so I'm going to go through how I worked it out. And there we go. So we've got 0.01 mole of a haloalkane E reflux with sodium hydroxide, which formed the reaction mixture containing organic product F. The excess sodium hydroxide is going to be neutralized with the dilute nitric acid. Then they added silver nitrate in excess, and that formed a precipitate G. The organic product F has a molar mass of 74 and a chiral carbon, so you can kind of work that one out. That's probably the easiest one to work out. So anyway, I'm going to show you here. This is my haloalkane E. Now, I put R groups around it. I don't know. They could be hydrogen. They could be CH3. They could be C2. Whatever. They could be any sort of things, those R groups. We know that's going to be attacked by a hydroxide ion because we know the reaction between a haloalkane and sodium hydroxide. We just did it earlier in this question, in an earlier part of the question. So we know the product is going to be an alcohol F, and we know that that has an MR of 74. So you could go ahead and work that out if that's the only thing you can do, and try and see if you can work that out. Now, I know that the precipitate is going to be a silver halide. So silver chloride's white, silver bromide's cream, silver iodide's yellow. They don't tell us the color of the precipitate, which is a bummer. Otherwise, we could have worked it out. But we do know that F has an MR of 74. So you could go ahead and play with some carbon hydrogen numbers and see if you can work that out, knowing that the carbon must be chiral that's attached to the OH. Okay, so you can probably work that out from that. Now, what we do know from this reaction, look, I've drawn it out. It's a 1-to-1 reaction. We know that. We've got it earlier in the stem of the question above. Now, that means that I know I've got 0.01 mole of product reactant, so I should get 0.01 mole of F, and I should get 0.01 mole of halide ions. There's only one halogen attached to the haloalkane. So now I can go ahead and use mass over moles equals MR and work out which is my precipitate. So silver has the AR of 107.9. Trust me, you can look it up in a periodic table, about 108. Now, if I add that to 35.5, you're going to get, what, 135.5 plus 8? What is that? Oh, my days, 143, something along those lines, right? So if I divide 1.88 grams, which is my mass, by 0.01 moles, which is how many moles of the precipitate I should have, I should equal 143 if it's silver chloride, 184 if it's silver bromide, and about, 234 if it is silver iodide. Let's check it out. 1.88 grams over 0.01 equals 188. You can see that is silver bromide. And you can check that by doing 188, which is your overall MR of your precipitate, minus bromide, minus 80, leaves you with 108, which is roughly Ag, silver. So G must be AgBr. We've got our first mark, and probably the hardest mark out of all of that. Okay, let's work out what F is. So we're going to work out the product F. Here, I've circled it in green. It's an alcohol, of course. Now, I could go CH3, CH3, CH3. Let's add that all up. We've got 15, 12 for carbon, 3 for hydrogen. So 15, 15, 15 for the 3 methyl groups. That's 45. Plus 12 for that carbon is 57. Plus 17 is 67. 74. That would make sense, right? It equals the same MR of 74 that we're told in the stem of the question. So could this be our product? No, it's not 2-mether, whatever that is, propan-2-ol. It's not, because we were told it had to be chiral. So what I need to do here is make sure that each of the groups attached to that carbon with the OH is different. So let's try CH3, CH2. Well, that's 29, 15 for the CH3, 14 for the CH2, 15 for the CH3, 17 for the OH, 1 for the H, add it all together, 12 for the carbon in the middle, and you also get 74, but this time we've got a chiral carbon. That carbon in the middle there is attached to 4 different groups, an OH, a CH3, a CH3, CH2, and an H. Now, I don't know whether they're going to be stingy and they're not going to like the way that I've drawn CH3, CH2, because I've shown the line attached to hydrogen. And even if I write C2H5, they might not like that. But I hate writing it in reverse with the carbon first, and I ain't going to bother. You can do that yourself if you want. So that's the second mark for F. Now, let's just check it out. What are we going to do for the original? Let's just copy F, but for E, for the third substance, but just swap the OH for bromide because we know it was a bromoalkane. And there we go. There's the 3 marks. Don't forget, sharing's caring, punch up the bell, subscribe. It's time to revise. Stereoisomers. This has got a bit of organic synthesis and a bit of electrophilic addition in it. Okay, cinnamaldehyde and methyl cinnamaldehyde are naturally occurring organic compounds. You can see they've both got a double bond. They've both got a phenyl group, benzene ring, and an aldehyde. Methyl cinnamaldehyde, this one on the right, is an E isomer. Explain this statement in terms of the Charning-Gold Prelog SIP rules. Pause the video, grab your pen and scrap paper, and see if you can write down 2 bullet points how you'd explain that the methyl cinnamaldehyde on the right is an E isomer and not a Z isomer. Basically, why is it an isomer? Okay, I'm going to go through the answers. So if you unpause, here we go. I'm going through it. Yippee-ki-yay. Right. They've told us we can write the methyl group as C6H5, or, well, I'm writing the phenyl group, sorry, not methyl, phenyl group as C6H5. Now, look, you would imagine that that is on top, kind of above the double bond, and that would make it a Z isomer because you'd have the 2 high priorities on the top. That would be Z, but they've told us here that it's an E isomer. So what I want to do is I want to flip around the phenyl group here because actually, although it is misleading from the skeletal formula, the phenyl group would actually be on the other side of the double bond. So it'd actually be like this. Now we need to go through and explain to the examiner why this, which I've drawn as displayed, is an E isomer. Now you can label the carbons around the double bond 1 to 2, but that can be misleading as well. You can call it A to B. However, you want to talk about them in order to be able to refer to them in your answer. Okay. It can be misleading to number them because you number the carbons in the naming of a compound. So, but the first carbon in the double bond, I mean the right-hand carbon in the double bond, has an aldehyde group above, which is higher priority. So the aldehyde group is a higher priority than a methyl group. You check the atomic numbers for that, and if they're the same like they are here, you go to the next atom, which is oxygen versus hydrogen. So the aldehyde is higher priority and the methyl group is lower priority. Now, again, I'm talking about above and below the bond. That's, again, a misconception because this is a planar molecule as there's no rotation around the double bond. Anywho, for references on this 2D diagram, I talk about above and below the double bond. So on the other, you can talk about other side. That's probably technically more correct. So on the other double bond carbon, on carbon 2 that I've labeled here as carbon 2, it's not really carbon 2 because this is a butte molecule. So on the other, or whatever it is, it's not a butte, but you know what I'm saying. Right, on the other carbon 2, the high priority group is on the other side. The phenyl group is below. Now, why is that higher priority? Because carbon has an atomic number of 6 and hydrogen 1. So the hydrogen is the low priority and the phenyl group is the high priority. So why is this E? E means opposite. It's German for entogen, E for entogen, which stands for opposite. And they're on opposite sides diagonally across the double bond. So you could say the high priority groups are diagonally opposite, or the low priority groups are opposite sides of the double bond. Either way to explain it would get you the marks. All right, let's move on. A student plans to carry out some chemical tests on both cinnamaldehyde and methyl cinnamaldehyde. Suggest a suitable chemical test to confirm that compounds contain an unsaturated carbon chain. So both of a double bond here and here. What test would you do? Pause the video. Have a go. Okay, you should know this one. It's the bromine water test. So that's orange to colorless. Bromine is red to colorless, but bromine water slightly diluted. It's aqueous solution, so it is orange to colorless as it joins across the double bond by electrophilic addition. Right. Describe a chemical test to confirm that both compounds contain an aldehyde functional group. Your answer should include the reagents and the observations. So 2 things to get 1 mark. They both got the aldehyde group. Now, what can test for the presence specifically of an aldehyde? And what tests for the presence of the aldehyde group? We have the silver mirror test, the Tollens reagent. So Tollens reagent, which is, what is it? Ammoniacal? No, it's not. It's silver nitrate in nitric acid, whatever it is. Is it ammoniacal? Oh, I don't know. You can leave in the comments if it is. You can just say Tollens reagent here, and then you don't have to try and list the contents of the Tollens reagent like I'm poorly doing over here. That doesn't even look like H. Oh my God, I put NHO3. It should be HNO3. Anyway, I'm an idiot. What are the results? You'll get a layer of silver atoms formed on the inside of the test tube, or you can say a silver mirror, hence the nickname silver mirror test. So your marks here really are for saying Tollens reagent and the observation, which is a silver mirror coating the inside of the test tube. Describe a chemical, or silver atoms coating the inside of the test tube. Describe a chemical test to confirm that cinnamaldehyde and methyl cinnamaldehyde contain a carbonyl group. How could the products of this test be used to distinguish between the two compounds? Use your answer, but do not include spectroscopy. So we can't say check it out on spectroscopy. Okay, guys, so you can't use fingerprint region and all that business. Okay, pause the video, have a go. Now, I'm going to go through the explanation. It'd be a mistake which some people may make if they pause the video and had a go. You may have said K2Cr2O7, potassium dichromate solution, acidified or something, where we go, was it green to orange with the aldehyde? But this would not change color with a ketone. So this is not the appropriate test to confirm the presence of the carbonyl group. Now, there is a test that confirms the presence of the carbonyl group. And it is 2,4-DNP, dinitrophenylhydrazine. And so 2,4-DNP, or 2,4-dinitrophenylhydrazine, reacts with both of these with carbonyl compounds, and it forms a yellow or orange precipitate, which is the product. Now, the product is a dinitrophenylhydrazone. So it forms a complex organic product when both of these react. Now, how would we decide which one? I don't know. This one's got branching, so I'm guessing it might have a lower melting point, right? It's got some sort of branching in it, but they're both going to form this phenylhydrazone, whatever, dinitrophenylhydrazone organic compound. What you can do is you can test their melting point and then compare to a data book which would have a list of those different organic products formed with 2,4-DNP, and you could specifically find out what organic product you have, and therefore you could trace back to what was the original compound based on the melting point of the product. So anyhow, how do you distinguish after doing 2,4-DNP? You check the melting point of the new product and you look it back, you look at a data book and compare and read up the melting point, and that should allow you to trace it back to the original reactant. Okay, gosh, that was long. Right, the flowchart shows some reactions with cinnamaldehyde. Draw the structures of the missing organic compounds in boxes and add the missing reagents on the dotted line. There's only really one reagent missing, I believe. Right, reducing agent. We've got NaBH4. You can leave a note in the comments if you can remember what that's called. You could use LiAlH4. What is it? Is it sodium tetraborohydride? Whatever it is. Okay, I can't remember off by heart. Right, anyway, those two kind of reagents are used for reducing. So what would you reduce an aldehyde back to? Well, you go back to a primary alcohol, wouldn't you? Aldehydes go back to alcohols, ketones go back to secondary alcohols. We're going to go back to a primary alcohol here. So you just got to think about, I need to add hydrogens on to take this back to a primary alcohol. So what am I doing? It's got to be all skeletal, but what I'm trying to do is I think there's going to be an extra diagonal line down. Skeletals are always a pain in the bum, right? So let me add up the carbons and then I can sort of work it out, right? Yeah, there we go. That's going to be correct. So you end up with kind of an extra line down because look, you've got 1 carbon, 2 carbon, 3 carbon, and then 4 carbon on the aldehyde. You're not losing any carbons, so you're going to have 4 here and then the OH coming off, whereas they have the CHO coming off. This time you've got to put the C as part of the skeleton, so it kind of looks like a longer skeleton, even though you've got the exact same amount of carbons. Anywho, there you go. There's your primary alcohol that's formed. Now, what reagent would turn this aldehyde into a nitrile? We're going to need to attack it with a CN, like with a lone pair. Yeah, we're going to need a nucleophile. And so we got to look at what nucleophile do we need and what reagent is going to give you those nitrile ions. Are they nitrile ions or are they cyanide ions? Again, you could leave it in the comment if you can remember if they're called nitrile or cyanide ions. Everything is escaping my brain today. You can see the lone pair on the Cn minus here is going to attack to this delta positive carbon because the oxygen's electronegative. Now, that means the carbon will not be able to maintain 5 bonds, so one of the oxygen bonds will break and the lone pair will go to the oxygen. This will make it negative. You normally draw this in 2 steps rather than 1, and that will attract to the hydrogen. Now, where did the hydrogen ions come from? That means we need to either have hydrogen as part of our reagent, or we need to acidify our reagent. So what kind of reagents do you think you need in order to do this? Of course, the hydrogen forms the hydroxy that you can see on the product, and the nitrile attaches there. Well, we're going to need to use HCN, hydrogen cyanide, which gives us those CN ions and those H plus ions naturally, but it's dangerous, need a fume cupboard, blah, 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 blah. HCN is very dangerous. So you could use KCN, potassium cyanide, or sodium cyanide. I guess you could use lithium cyanide. They normally do KCN, but you'd have to acidify it. So you could say with H2SO4 or some sort of acid, okay? Or you could just put H plus in brackets. Hopefully on the mark scheme, they allow that, or write acidified KCN. And that's to supply the hydrogen ions to form that hydroxy group. Okay, let's look at this next one. What we're doing, we're going down here. Now, this one has got a super complex mechanism that you definitely don't need to know off by heart. But essentially, you're going to hydrolyze. We're going to go down here with those hydrogen ions, which stand for an acid. So this is acid hydrolysis. You get your lone pair from the water attacking the carbon. And then slowly by slowly, each one of those triple bonds in each step of this mechanism breaks. And eventually, you get ammonia eliminated. The nitrogen leaves, and you are just left with a carboxylic acid group. So we're still going to have the alcohol, but what we're going to have down here is a carboxylic acid, so an OH and the C, the carbonyl bond there. So you're going to have a carboxylic acid basically, and that's what you get when you use acid hydrolysis of a nitrile. When you do acid hydrolysis of a nitrile, you are going to get a carboxylic acid, and that the mechanism for that is dirty. It's like 4 steps, which shows how each bond is broken. So I don't think you need to know that. So I'm not going to go through the whole mechanism for that. But you do need to know that on a revision card. Acid hydrolysis of nitriles give you a carboxylic acid. Now here we're going to use excess hydrogen and nickel. This is like hydrogenation. We're going to reduce the nitrile group to a hydroxyamine. Now, adding hydrogen with a nickel catalyst, I'm not sure. I think you might get rid of the double bond here as well. I just need to double check on that. But we're definitely going to reduce the nitrile. And I'm just wondering whether it would also, you can use a platinum catalyst for this. They've used nickel here. You can use a platinum catalyst. I don't know if you can use phosphoric acid. Can you use phosphoric acid for this one? Maybe. But anywho, hydrogen with a nickel catalyst, you're going to get 2 hydrogen molecules because you're going to break that triple bond. You need to add 2 hydrogens to the carbon and 2 to the end to make an amine. So you're using 4 hydrogen atoms altogether. Now I'm just going to redraw it and put CH2, NH2 as my final group there. Or you could just do skeletal and then NH2. Now, you're not going to hydrogenate the benzene ring. We're not dealing with just like a cyclohexene or something. So what we got going on here is far more stable, the benzene ring. Okay, what we got going on, you could write it like that. Should I write it like that? NH2? Kind of like that, or shall I include the carbon? Now I should get rid of that double bond. That double bond is going to have hydrogens added across it, so I'm going to want to get rid of that double bond, and I could probably just put NH2 like that. You got to add up how many carbons there's going to be, and maybe I'm going to put CH2 NH2. That might be a little bit better. Oh, I got to get rid of the double bond. Yeah, there we go. So remember that the double bond gets hydrogenated as well as reducing the nitrile to amine. I think the mark scheme likes you to write like this, CH2, NH2, like that. Alrighty then, that's all of them marks. So let's move on. Whee, seriously long question this. That was pretty difficult, I reckon. Anyhow, right, zing, zing, zing. I hope you're revising hard for your A-levels. Remember, A-levels all about that hard revision. So, methyl cinnamaldehyde reacts with iodine monochloride ICl by electrophilic addition. The reaction produces a mixture containing 2 different organic products. Here we've got methyl cinnamaldehyde. Electronegativity values of chlorine and iodine given in this table. This is the old Pauling scale. So, chlorine is more electronegative with a 3.0 and iodine 2.5. Outline the mechanism using the curly arrow model for the formation of one of the organic products and explain which of the 2 possible organic products is more likely to be formed in your mechanism. You can show the phenyl group as C6H5. Thank you very much. Now, what I want you to do is grab a pen, grab paper. This is a nice one. You just got to show that you know how to do electrophilic addition. Go! All right, I'm going through the answers. So look, the Pauling scale, chlorine is more electronegative. It drags that dot and cross, that electron shared pair towards the chlorine more than towards the iodine. So what happens is chlorine becomes negative, the iodine becomes positive. Now I've drawn a benzene ring. I hate the Kekuli structure for the benzene ring, so I tend to draw that. However, the issue is that they told me to use C6H5, so I'm a bit stupid anyway. I could have just used C6H5. Now, the carbon is slightly positive, so the iodine is going to no, nothing to do with that. The iodine is slightly positive, the chlorine is slightly negative. So yeah, this is the lone pair moving. I'm using a nice little pink here. Make sure you get a nice curl like that on your arrow, because they get a bit funky if you don't do curly arrows. And these are the two curly arrows. So lone pair goes from the double bond to the delta positive iodine, not the other way around. Remember, it's electrons that move, not protons. So, and then the chlorine has to break off because the iodine can't have two bonds. It's group 7, it can only have one bond. So that bond's got to break off. That's going to leave us with a chloride ion. I'm going to show the phenyl group as C6H5 for the intermediate, okay? Because it's a bit long drawing that benzene ring, and they're giving us permission, so why not? So here we go. Here is where the iodine's joining on. I'm joining it onto the first carbon in the double bond when the double bond's broken, and I'm leaving the second carbon positive. Now, we don't call that carbon a carbocation, but the whole molecule is now a carbocation. So that is the positive carbon uh, on the carbocation, which is the whole molecule. So now my chloride ion will attack this positively charged carbon atom, and a bond will form there. And I'm not even going to attempt to name this. If you want to name this molecule, this product, it doesn't ask for that. You don't need it for your 6 marks, but you could try and name it. I mean, the aldehyde's going to be the most important, right? It's going to be like, so it's going to be like propanaldehyde. Oh my days. Is that 2-chloro, 3-iodo, 3-phenyl propanaldehyde, something like that? That's absolutely disgusting. I'm not going to name that. I'll let you guys do that if you want to in the comments, and then you can fight it out and see who's right. Right. The other one is if the iodine added to the second carbon on the double bond, and our carbocation has the first carbon in the double bond positive like this. I called it a double dond. I don't know what that is. No, did he? Right. Okay. Here the chloride ion is going to attack here. So for this mechanism, you're going to get a mark for showing that the iodine's delta positive in the chlorine, because they got us to use the Pauling scale for that. You're going to get marks for the curly arrows. So I'm going to put us on about 3 or 4 marks at the moment, because we've done the whole mechanism. I haven't shown the product, and they can be a real stickler for that, which means long this, I've got to redraw out one of the products. So I'm going to redraw out the major product, because that's what they're like in the exam board. It depends which exam board you do. Now, weirdly, the AQA exam board, or not weirdly, they just go, well, yeah, we know you know how to draw the product, because the chlorine would be attached where you've the positive charge. So we're not going to get you to redraw the whole thing out. But if you're doing OCR, you will need to draw out the full product, even though it's kind of a lot of repeat. You're just adding the chlorine on where that positive is and getting rid of the minus and the plus. And there you go. That's another mark for the product. So there we go. Now what we need to do is explain why this one is major. And there's 2 ways to attack this. We could say this carbocation is more stable because it has this alkyl group attached, right? CH3 or C2H5 groups, ethyl and methyl groups. These are or propyl groups. These are alkyl groups. They're kind of electron donating, or is it an electron inductive effect, whatever it's called. And they stabilize the positive charge. They make it less positive because their electron cloud goes towards the positive charge. So the more alkyl groups or R groups you have, the more stable you are. And so we could say that. Now, we could say that this one is less stable as it has no alkyl groups directly attached to that carbon. There's no methyl, ethyl or propyl groups attached to the positive carbon. There is a phenyl group, but I think we can remember that phenyl groups are electron withdrawing. That benzene ring might withdraw the electrons off the carbon and make it even more less stable. So we could argue it in those terms, and some people might like to go down that kind of route, talking about alkyl groups and what is more stable. But you could also use Markovnikov's rule. Now, Markovnikov's rule is going to explain which carbocation forms. So technically, the halide, the first halide, or when you have a halogen, so if it's bromine or whatever it is in iodo, whatever, what was this called? iodine monochloride. Right, so it's made of 2 halogen atoms. Right, the first halide will attach to the carbon with the most hydrogens on it, and that's like Markovnikov's rule. So the first halogen, in this terms, iodine, will attach to the carbon that has the most hydrogens on it, and the one on the left-hand side of the double one is only got 1 hydrogen, but the other one has no hydrogens attached. So you could do it like that, or you could say the chloride will attach to the carbon with the least hydrogens on it. So it's going to, the chloride is the second one to attach, and it attaches to the one with the least hydrogens on it. So there's different ways to argue it. Some people like the Markovnikov's rule, and that is that the first halogen, or the halide, will attach to the carbon with the most hydrogens on it. And there you go. And that will form us our lovely carbocation, and that's why that one is the major one. So there's kind of 2 different ways to argue it. Talking about alkyl groups, stabilizing the carbocation, and you could mention primary, secondary, tertiary carbocations if you want, depending on the number of alkyl groups. But that's going to get you all of the marks. Don't forget sharing, caring, hit the like, punch up the bell, subscribe. Let's get to the marks. I'll catch you lot on the next video. Let's smash the chemistry exams. Let's go, people. We're going through something about aromatic carboxylic acids and their derivatives. The flowchart below shows some reactions of compound H in the boxes. Draw the organic products of these reactions. And you can see compound H is in the middle. It's a carboxylic acid. We've got a hydroxy group, or it's a phenol with a carboxylic acid group coming off, however you want to call it. Carboxylic acid will take the priority. We've got sodium carbonate reacting with it. We've got sodium hydroxide solution reacting with it, and bromine. See if you can work out the 3 products. Why don't you pause the video, grab your pen, paper, have a go, and then unpause and watch the explanation for each. Here we go. Okay, so let's start by copying out compound H in the box. I'm a bit of a rubbish drawer, GCSE level 4 art. I've told you about that. Now, the sodium ions are going to react. We're going to get this carboxylate ion, sort of sodium ethanoate ion, or sodium whatever carboxylate ion there. Now, why does the carbonate ion not remove the hydrogen from the hydroxy group? Well, carbonate ions are not strong enough bases to remove the hydrogen from the hydroxy group. Why can they remove it off the carboxylic acid? That's because of that other oxygen on the carbonyl group there, which is making that carbon delta positive. Okay, now we've got the same situation going on here. The only difference is that our base in this situation is not a carbonate ion, but a hydroxyl ion. And the hydroxide ion is a stronger base than the carbonate ion, and it can remove the hydrogen on the hydroxy group. And so we get that. You can put brackets around the Na plus or not. It's up to you. Now, bromine, it's not going to be able to do nucleophilic substitution and swap for the OH like with a haloalkane. Not unless where you can form haloalkanes with alcohols, you can do nucleophilic substitution, but you would need a catalyst, as they always prefer the OH group to the halide group. But what you will get here is the bromine molecule being polarized as it approaches that electron-rich, dense, delocalized pi cloud there in the middle. And that means that we are going to get some of the hydrogen substituted for the bromine. As you can see, now the bromide ion that's left over, the Br minus, is going to get repelled. So that is not going to happen. But we just want to substitute one of those hydrogens for a bromine atom and make sure it's the right one. And that's going to get you to 3 marks for the first part of the question. Let's zing down and do the second part of this question. Okay, actually, where's the question? There it is. Compound H is used to synthesize a polymer I, as shown in the flowchart below. Complete the flowchart by drawing the structure of the acyl chloride and the 2 repeat units of polymer I in the big box below, and we need the acyl chloride on the right here. And state the formula of the reagents, if it's plural, required for the first stage on the dotted line. All right, guys, you know what to do. Pause the video, have a go. It's worth 4 marks. Let's get into it. So first up, what's your reagent? We need to replace that OH with a Cl. So we're going to use thionyl chloride, THIO. NYL, and it's just one of those weird things. It's a chlorinating agent. It's got a very acrid smell when you use that in the lab, but it's a chlorinating agent, and the formula is SOCl2. You just got to learn that off by heart, okay? So it's a chlorinating agent, great for forming acyl chlorides. Don't get it mixed up when you use your halogen carrier to make the electrophile, the really strong electrophile, when we use acyl chlorides and AlCl3. Okay, what we're going to do here is just replace the OH with the chlorine, and that is our acyl chloride. So lovely jubbly, that's going to get us 2 marks, one for the reagent, one for the correct structure of the acyl chloride. Here we're going to get 2 marks, a little bit more complicated. You want to draw 2 of these next to each other, and then you want to remove the H and the Cl. Now, normally if it was a carboxylic acid there, we'd remove H and OH, condensation reaction, removing water. But with acyl chlorides, you're removing a chlorine and a hydrogen, so you're going to remove hydrogen chloride. Draw 2 of these molecules and remove 2 HCl's, and you should be able to work it out. So you're going to remove the H of the hydroxide group, or the phenol, whatever you want to call it. And then we're going to remove the Cl, and then we want to join another one on where the same thing has happened. So we're just joining the O from the hydroxide group. I'm drawing it in pink here of our second acyl chloride, and we're just going to keep that continuation going on. Now, I will just leave that off. I don't want to write an O on that side because I've already removed 2 H's and 2 Cl's. I think the brackets are probably optional on the mark scheme, but I'm going to use brackets. I probably should put an N outside the brackets as I won't get both of the marks, but there we go. Let's sing on. Okay, so in this next question, let me get it into focus. Ain't no hocus pocus. A cosmetic product containing 4 esters, J, K, L, and M, is analyzed by gas chromatography and mass spectrometry. The results are shown below. Here's the gas chromatogram. We got the retention time 1, 2, 3, 4, 5 minutes. And then we have the relative molar proportions 4.2, 4.3, 1, and 5.9. So essentially, as good as we need, they are the moles of each of these products. So we got 4.2 moles of J, 4.3 of K, and 5.9 of M, and 1 of L. I know they're not the actual moles, but they're relative to each other. They are the moles. We got the mass spectrometry here, and we've got the MR, well, the MZ value, which is equivalent to the MR in this situation. And so we have J is 152, K is 166, and L and M are 180. The concentration of ester K in the cosmetic product is 9.13 times 10. What is that? Is that to the minus 2? Okay. G per dm3. Using the results, calculate the concentration in mole dm minus 3 of ester M in the cosmetic product. Give your answer to 2 significant figures. We need to work out the concentration of M in moles per decimeter. We've been given the moles in grams per decimeter of bada bada bing bada bong K. Why don't you pause the video, bust out the calculator, and have a go? Well, I'm going to go through the answers for you, folks. So what we want to do first of all is we want to take K and say, well, look, its MR is 166. We're going to want to think about our triangle. We're going to want mass. They haven't given us the MR just for the sake of it. We got to use it. So we're going to do mass over MR is going to give me moles. So I'm going to do 9.13 times 10 to the minus 2. And that is going to be divided because that's grams. So we're going to divide that over the MR. And that's going to give me moles in every decimeter. And that's going to give me something like 0.00055, and that's going to be moles per dm, and that is for substance K. And you could write that as 5.5 times 10 to the minus 4 mole per dm of substance K. Now, what we need to do next is work out from this how many moles we have of substance M. And this is where we're going to bus up to the top and use the ratio. Don't forget to help me out and hit the like, peoples. It massively helps me. So hit the like if you like the video. A general structure to esters J, L, and M is shown below, where R is an alkyl group. You can see there's an R coming off the O. Use the mass spectrometry results to deduce the possible structures of J, L, and M. So we know that J has an MR of 152, L 180, and M 180. I'm going to write those on the side over here. We're going to need those when I scan back down, and we're going to draw the structures and work it out. So we know the total MR of the complete molecule when it's J is 152, L 180, and M is also 180. Looks like they are an isomer of each other, L and M. Now, let's get on. We've got to work out the structures of J, L, and M. We know that the R group is going to be the variable factor. Let's work out what the constant MR is between all of these, the constant fragment MR here, and that is a benzene ring, normally C6H4, but there's two substitutions on it, so I'm going C6H4, which is 76. I've got the O and the H. If you add up their masses, that's 17. I've got 16 for each oxygen, 12 for the carbon, 44. If I add 44, 17, and 76, I get 137. I know the constant region for all of these is 137. So for J's R group, I'm going to do 152 minus 137, and that is going to give me 15. And what possible bit, we want to make an ester, so we could have methyl, ethyl, propyl, butyl, whatever. It's going to be the methyl group. The methyl group, carbon's 12, each hydrogen's 1, that's 15. So we're going to have a methyl group stuck on where that R is. So we just need to draw that formula out, smash in the CH3. Now check out my level 3 GCSE artwork here. But there we go, folks. I've never been very good at drawing, so I'm just about squeezing that in the box. No diddy. And that's CH3 right on the end there, 1 mark. Now let's check out the next one, L. We're going to do 180. We're going to take away the 137. The R is going to give us 43. Now it's going to be the same for M as well. Let's work that out. Now we know that the methyl was 15. Let's just check out naturally what's an ethyl group. Okay, so an ethyl group is 2 times 12 plus 5 is 29. So it can't be the ethyl group because we need it to get to 43. And if you just go one stage up with your side group to a propyl, you'll find 3 12s are 36 plus 7 is 43. Boom! We found our answer. We need to add a propyl group on. Now, they might let us put C3H7 in the exam. I'm probably not going to be able to squeeze this in here. This is pretty grim. Bada bada bing, bada bong. Yeah, you probably should put CH2, CH2, CH3 neatly together. I am not going to be able to fit these in, so I'm going to kind of, what am I going to do? I'm going to kind of draw down. Now, you want to try and make sure you fit it in. You could probably like draw it diagonally, whatever. Yeah, I just need to fit these in here. So CH2, CH2, CH3. I know it's not exactly proper, right? But the exam board generally say make sure it's unambiguous. It's really clear that's a propyl group attached. They might even let you have C3H7, or you could probably do CH2 in brackets to, or CH3, yeah, and 2 CH2s, whatever. Right, so what can M be? Well, M has got to be the same thing. It's got to be a propyl group, but arranged differently, right? It's an isomer. So we just want to change the chain here a little bit. And what we're going to do is we're going to have, I've written that as 2 CH2s. We're going to have 2 CH3s coming off, and it's joining onto the middle of that propyl group there. So that's no longer propyl anyway. But yeah, same thing, same amount of carbon, same hydrogens. We've got 7 hydrogens and 3 carbons. And there you go, guys. That is the other version and only other version we can have. I don't know whether it's best to write CH3 2 with the brackets or whatever, but I've just tried to show the examiner I know exactly what the structure is, and they should give me the marks for that. So let's give ourselves another 2 marks. And don't forget, sharing's caring. Hit the like, punch up the bell, subscribe. I'll catch you lot on my next vid. The relative molecular masses and boiling points of some fuels are shown in table 22.1. We've got hexane, pentane, 1-ol, and heptane. Write an equation for the incomplete combustion of heptane. Explain the difference in the boiling points of the fuels in table 22.1. Why don't you press pause on the video, grab a pen, grab some paper, have a go at this one, and then I'll go through how to get all 5 marks. Let's get into it. Okay, so we know we're dealing with heptane here, so we want to write C7H16. Now, why do we know it's H16? You should remember the general formula for alkanes, and of course, CnH2n plus 2. That's the general formula for the old alkanes. So once you know that, then you can easily work out the formula of an alkane. And of course, it said incomplete combustion. So we're going to need some oxygen, even though it's incomplete. Now, do we form carbon monoxide or carbon dioxide? Well, we form carbon monoxide when it's incomplete combustion, and we form water. Now, I think technically on the mark scheme, I might be allowed to just write solid carbon soot. So just carbon might make it easier for balancing. But and I think they'll accept either question, because sometimes you get carbon monoxide, sometimes you get carbon, sometimes you get both. So maybe if we'd included carbon and carbon monoxide. Anyway, easier to do it like this. Because there's a 7 in the C7H16, that means you're going to get 7 CO2. So the ratio of the organic compound to the carbon dioxide or carbon monoxide is always going to be like 1 to 7 here, because it's heptane. And then don't forget there's 2 hydrogens in water, so you're going to need um, 8 waters to make the 16 H's. Yeah, that's all good. Right. 7.5 oxygens to balance it all up. Explain the difference in the boiling points of the fuels in table 22.1. So you should have gone through this already. I've circled hexane and heptane. They're both alkanes. Okay. They're just made of carbon and hydrogen. They're going to be non-polar because there's not a big difference in electronegativity on the pooling scale between carbon and hydrogen. So you don't get dipoles formed. But you do get random instantaneous dipoles from the random movements of electrons, right? Instantaneously forming and breaking every second. Millions of them. And these will mean that there are some forces between hexane molecules or between heptane molecules. And these are called weak intermolecular forces. Now, at A level, we need to name them. You can call them van der Waals forces, although that includes temporary dipole and permanent dipole forces. They both come under the umbrella of van der Waals. For the sake of speed and brevity, I've written VDWS. You can't write that in the exam. You have to write, at least use the name of a force once before you start using abbreviations. Or you can call them London forces. Now, these are weak and easy to break, hence the lower boiling points of the hexane and heptane when we compare them to the alcohol pentan 1-ol, which has hydrogen bonds. You need to point out that hydrogen bonds or H bonds are stronger than London forces or van der Waals forces, and therefore they take more energy to break, hence why the alcohol has the higher boiling point. Now, if we go back to heptane and hexane and we say, okay, why does heptane have a larger boiling point than hexane? Why is it 98 to hexane's, what is that, 69, or 96 to hexane 69? And the reason is heptane is a larger molecule, more electrons, therefore more random movements of electrons, more instantaneous dipoles are set up, stronger van der Waals forces, more energy required to break. Okay, now we're going to look at C. Fuel additives are often used to improve the combustion, of a fuel. I really need to get some new glasses. Compound N is a fuel additive containing carbon, hydrogen, and oxygen only. Complete the combustion of 1.71 grams of compound N produces 2.97 grams of carbon dioxide and 1.62 grams of H2O. The relative molecular mass of compound N is 76, so that's its MR. We've got the mass of the CO2, 2.97, the mass of the water, 1.62. We've got the mass of compound M, which contains carbon, hydrogen, oxygen, 1.71 grams. Calculate the molecular formula of N and suggest a possible structure for N. And how much is that? 5 marks. Jeez! All right, people, press pause on the video, have a go at this one, and then on some scrap paper, then unpause, and we'll go through it. Okay, so we want to first of all find out how many moles of N do we have. Well, I've got 1.71 grams of N. N's got carbon, hydrogen, and oxygen in it. It's not really a hydrocarbon, even though I keep referring it to, I can't even speak properly now. Anyway, so we're going to do mass over MR gives me N for number of moles. So 1.71 divided by 76 equals 0.0225 moles. So now I know I've got 2 moles of my hydrocarbon. Imagine when you're going to combust it. If you have 1 mole of methane, right? How many moles of carbon dioxide would you make? Well, you'd make 1 mole of carbon dioxide, 1-to-1 ratio between the carbon dioxide and the number of carbons. So the number of carbon dioxide molecules comes from the number of carbons in the hydrocarbon, or the fuel, I should say. So C4H6O3, let's just make that random formula up, would make 4 lots of carbon dioxide. So if I can work out the moles of carbon dioxide, divide it by the moles of my fuel, I'll find out how many carbons are in the fuel. So we know that we have got 0.0225 moles of the fuel. What I need to do is find out the amount of moles of carbon dioxide. Now, the ratio between the fuel and the carbon dioxide gives me the number of carbons in the fuel. So you can see in my little equation I've done there, C4H6O3, whatever the hell that is, goes to CO2. The ratio of the carbon dioxide molecules to the fuel is 4 carbon dioxides to 1 fuel, and that tells me there are 4 carbons in the fuel. So let's do 2.97, which is the mass of CO2, over the MR of CO2, which is 44, 12 for the carbon, 32 for the 2, 16 oxygens. And if you divide 2.97 by 44, you're going to get 0.0675 moles of carbon dioxide. Let's take that 0.0675 moles of carbon dioxide, divide it by the moles of the fuel N, and N is the fuel N is 0.0225. So 0.0675 over 0.0225, we get 3. So the ratio of carbon dioxide to moles of the fuels is 3 to 1 to moles of N. So I've got 3 carbon dioxides compared to 1 mole of N, which is the fuel. That means there must be 3 carbons in N, the fuel. So I know the formula is C3 for the fuel. Let's do the same with water. Now, water is 1.62 grams divided by 18, 2 for the H is 16 for the oxygen, and that gives me 0.09. Let's do the same thing, divide the moles of water by the moles of fuel. 0.09 over 0.0225 is 4. That means I've got 4 water molecules for every mole of fuel. Slightly different than carbon dioxide here, because that's 4 times H2. That means that my fuel must be H8. Because if you've got 4 moles of water compared to 1 mole of fuel, that means there were 8 hydrogens in the fuel, because 4 waters is 4 H2O. So now I need to work out my oxygen. You might think, do I need to balance up and work out the moles of oxygen? No. I've got the MR, which was 76 of my fuel. I now know I've got C3H8O something. So I'm just going to do 36 for the 3 carbons, 8 for the hydrogens, that's 44. I'm going to do 76 minus 44 gives me 32. 32 is the amount of the MR left that is devoted to oxygen. And guess what? Each oxygen atom is worth 16 atomic mass. So that means I've got 2 oxygen atoms in that formula. So the formula is C3H8O2, and that has given me 4 out of those 5 marks. I'm absolutely happy with that, because that's A star. Remember, 80% is going to get you into the A star region normally, not always. Sometimes we need even higher, 85, when the exam board is being brutal. But I'm going to try and work out a formula now. Just try and work out a possible formula. So I've got 3 carbons, H8s. Oh, if I do a carboxylic acid, it's got the 2 O's, but it's only got 6 hydrogen. That is not the formula. That's not the possible structure. Let's try another. So I've got CCHH. All right, I've got 3 carbons going on here. I got 7 hydrogens. Let's put an OH there. That's 8 hydrogens, 3 carbons, but 1 oxygen. No, I need to smash another oxygen in without changing the number of hydrogens. I need this kind of ether. It's called an ether, kind of oxygen with the O banged in the middle of the carbon chain. I've kind of messed that up, haven't I, as well? Let me draw it out in the box where we're supposed to put it. And I think I've cracked it now. I'm going to need, when you just need to add an oxygen into a carbon chain, just stick an O in the middle of the carbon chain like that, and you don't have to add any hydrogens on or anything. And that looks like my perfect formula. 3, 4, 5, 6, 7, 8 hydrogens, 3 carbons, 2 oxygens. Boom! We've solved the formula, peeps. That is compound N, or one of the possible structures for compound N. Beautiful. And that'll get you all 5 marks. All right, moving on to the next little question. Let's go. Let's clear that screen and move on, folks. Don't forget to hit the like. It massively helps me out. I massively appreciate it, because it takes me a long time to do these. Right, sol keto has been investigated as a potential fuel additive. Sol keto is synthesized from propane, 1,2,3 triol, and a carbonyl compound. Construct a balanced equation for this synthesis. Show structures for the organic compounds in your equation. It's kind of best to use skeletal, but they allow you to use structural or displayed. Yeah, propane 1,2,3 triol. Essentially, that's like glycerol when you're dealing with biology and you're talking about fatty acids, and glycerol make lipids or triglycerides. Yeah, same kind of thing. So, oh gosh, I'm terrible at writing out skeletal structures. I just have to imagine there's a carbon at the end of each point. except for where you have a functional group. So I think this looks like a McDonald's M. I don't know what the hell I've done there. Anyway, that's my propan. Oh, I'm going to leave it, right? I can't get my brain around that. That's propan 123 trial. Now we're going to add a carbonyl compound, and it's going to be propanal is going to be the most suitable one to add. And I'm going to show you why we know it's propanal. So it said carbonyl compound, so I know it has to contain the carbonyl group, which is the C double bond O. Count up the carbons in propan triol is 3, and then if we count up here, our final product, sol-ketal, has 6 carbons. So I knew that it's a carbonyl compound with 3 carbons. So it had to be propanal or propanone. Sorry, this is propanone I've drawn. So it had to be propanal or propanone. And if you look at the structure, it's going to end up being propanone rather than propanal. And so I'm going to draw the final structure, which is the sol-ketal, which I'm just copying from up there. Now, whether the exam board say I have to do that. Oh, we have 3 oxygens here and a 4th on the propanone, but only 3 in sol-ketal, which means we need a 4th oxygen missing somewhere in our products, which means I'm going to use H2O. Sorry about the interruption. Yes, darling. What do you want, babe? Okay, yeah, so you know that we've had a condensation reaction here and we've produced a water molecule, and you can tell that because we've got 4 oxygens in our reactants. We've only got 3 in our sol-ketal, I can't pronounce it, and so we've got an extra water molecule left over. All right, enough of that. That's going to get you the 2 marks. Let's get on to the final bit, and the bit that people find the most tricky out of all of this. So we've got all of this information here. A scientist is researching compounds that might be suitable as a fuel additive. I can't speak. One of the compounds gives the analytical results below. We've got elemental analysis, we've got mass spectrum, we've got the H1 NMR in D2O. The number of the peaks are the relative peak areas, the numbers next to the peaks. And then they said they ran the spectrum without D2O after, and 2 additional peaks appeared. 2 additional peaks appeared. Gosh, I'm losing the will to speak. The ability to speak. Use the information provided to suggest the structure of the compound. So we're going to use all of this info, and it's a fat 6 marker. I'm going to use all of this info. I'm going to scribble all over the page and show you how we're going to work out this structure. Let's get into it. I would grab a pen if I was you. You might need your data book so you can look up the ppm. You can do it without the ppm, really. You can do it with all the information that's given here. You can do it without the data book, and you can work out the structure of this. Let's get into it. Pause the video, have a go, and then I'll go through the answers. Okay, so the first thing I'm doing is the empirical formula. Why am I doing that? They've given us elemental analysis by mass. You just pretend the percentage is grams. So 54.54 over 12. That's like mass over MR or AR, however you want to do it. And that gives me 4.54 moles. It's really just a ratio, but we can call it 4.54 moles of carbon. And then we're going to do 9.1 over 1 gives me 9.1 of hydrogen, and 36.6 over 16 for oxygen gives me 2.27 something something something. Now divide all by the smallest, so 4.54 over 2.27, 9.1 over 2.27, and 2.27 over 2.27, and you're going to get the empirical formula, the simplest whole number ratio. Sometimes you have to multiply to get it into whole numbers because you'll get like 1.5s and that when you divide by the smallest, but we don't have to do that here because it does work out as carbon 2, hydrogen 4 when you divide by the smallest, and then just oxygen is 1. So C2H4O. Now we're going to get a mark for that. We've worked out the empirical formula. So out of the 6 marks, I'd say that's going to get you a mark for that bit of analysis. Now we need to use the MZ ratio from the molecular ion peak. That's the final line on the mass spectrum, which we don't have here. It's 132. Now, if we add up the empirical formula, we get 24, 4, and 16 is 44. We know the molecular formula, when added up, equals 132 because that's the MZ ratio. So we're going to do 132 divided by 44, kind of molecular MR by the empirical MR. You could think of it like that. And that gives us 3. So 3 lots of that empirical formula go in the molecular formula. So just times by 3 and you're going to get C6H12O3. That's your molecular formula and probably bags you the second out of the 6 marks. And then now we're getting into the H1NMR. These numbers represent the amount of hydrogen. Now, if you add them up, they only equal 10 hydrogen, but there's 12 in our molecular formula. Where's the 2 missing hydrogen? Well, they did it with D2O, and the OH peaks disappear when you do that. So there would be 2 additional peaks, which they tell us about down here. And those 2 additional peaks will be the 2 missing OH groups. We know it's not NH, which can also go missing when you use D2O. And we know it's not the NH because there's no nitrogen in the formula. So it has to be 2 OH peaks that are missing. And that would account for the 2 hydrogens that are missing when we add up the relative peak masses. So when we add up the 3, the 6, and the 1. Now I'm going to start over here analyzing this first peak, working from right to left. So going from 0, I reckon that's about 1.2 ppm. I could be wrong as the chemical shift. And I'm going to look at that first peak, and it has a 3H, which tells me there are 3 hydrogens in the environment. I'm probably looking at a methyl group, right? One of the hydrogens on the methyl group is giving me this data. And it is a doublet. There are 2 peaks on that graph. You can't really see it because it's so small, but there are 2 little peaks there, and that tells me that the CH3 group is adjacent to a carbon with 1 hydrogen on it. The splitting pattern is the like N+1 rule or whatever. So what is it? Yeah, N-1, whatever the rule is, I can't remember. But basically, if it's a doublet, it means that there's a carbon with 1 hydrogen on adjacent. So I would write it like that. That's my fragment that I can get from that first bit of information. Now we look at the second piece of information. Look at that second peak working from right to left. I don't know, what is that, 1.3, 1.4? It's just before the halfway between 1 and 2. So just before that. So yeah, maybe 1.4. So ppm or 1.3 ppm. We'll see that it has a relative peak area of 6, meaning there are 6 hydrogens. So I'm looking at 2 CH3 groups connected to a carbon. Now it's a singlet, just a straight line, which means there are no hydrogens. So you kind of do N-1 rule, like singlet. There are no hydrogens attached to the carbon that's adjacent to these 2 CH3 groups. So I'm expecting 2 CH3 groups on a carbon that has another carbon attached with no hydrogens on. Minimums has another carbon attached with no hydrogens on. So we're looking at 2 CH3 groups attached to a carbon, and there shouldn't be any hydrogens maybe on that carbon, or it should have one of the groups is not a hydrogen. We know that for sure. Okay. So it could be like that. It could also be CH3 with up and down, and then yeah, a carbon on each side, and one of them has no hydrogen on, at least one of those. And then we go to the final bit of information. Now you'd have to zoom in close to this to see whether it's a quintet or a quartet. This is actually a quartet. If it was a quintet, it'd be a multiplet, and it would tell us like that you had a CH3, CH2 or something like that. But this is, or sorry, it was CH4, so 2 CH2 groups or something like that on either side. But it's not. This is a quartet, and that tells me that there's a CH3 group attached. So the quartet has a 1 hydrogen in the environment. So we're looking at, really, that's that first fragment we looked at. That's that CH telling us that it's next door to a CH3. So I've circled the H there. That's what gave us that quartet, that H. And it was basically saying, look, I'm a quartet splitting pattern, so I'm next to a CH3, but I've got a 1 as my relative peak area. So there's only 1 hydrogen on my carbon. Now, we know there are 3 oxygens in this compound, right? Because the molecular formula was O3. We know that 2 of the oxygens are taken up with the OH groups that created the 2 peaks when D2O was taken away. We saw these 2 peaks that represent OH groups. Now, when that means that there's 1 more oxygen that is not on an OH. It can't be 3 OH groups. Otherwise, there'd be 3 peaks appear when the D2O was removed. So it's either going to be a carbonyl oxygen or one of those ether kind of oxygens that we did earlier, which is within the carbon chain. You just randomly jam an oxygen in there. So let's try and work out some sort of compound. So I don't know, I've got CH3OH. Could bust a little double bond somewhere. Why am I busting a double bond? I want to soak up some of those hydrogens, because look, it's C6H12. It's not C6H14. I'm going to need to get rid of some hydrogen. So I think that's all right. Is that all right? Yeah, that might work. I don't know. I'd have to check the mark scheme, which I don't have on me at this secondo. That would represent that. That would represent that down there. If I circled that, that would look all good. Those would be the two missing OH groups. I got a kind of ether O there, and I got a CH3 there. Yeah. Yes, I should have had some singlets from that CH3 attached to the O. Well, they're not attached to a carbon, so yeah, that might be doable. I don't know. I'd have to check the mark scheme. Let's try another one. See if we can build up another one. It'll be very similar because you just got to piece all of this together and then check your molecular formula and make sure it works. Make sure you've got 3 oxygens. Make sure you've got those fragments that you've identified from the splitting patterns, right? Because that's what the exam board are going to do. They're going to say, have the bits that you identified, have you included them in your model? So let's go with the 2 CH3s that we got from the second peak with the 6H, that one there, the second peak with the 6H relative area. That could be like this, a carbon in the middle and 2 CH3s, one off each end. Now it was a singlet, so we know that it has to be attached on one side to a carbon with no hydrogens. But that doesn't mean that I can't have a carbon on its left-hand side here in green with 1 hydrogen. And this left-hand side would represent that peak, that first peak at 1.2, the one with the relative area of 3, right? That would tell me that kind of section that we worked out, which is adjacent to the CH. And that is the quartet peak. This little green one is the quartet peak with the CH there. Now, it's got one of those OHs attached. And okay, so that looks pretty good. Now, I need to have a carbon with no hydrogens attached here, which is why I got the 6 and the singlet, the relative area of 6 and the singlet. And the way I can do that is by doing a carboxylic acid group at the end, because there's no hydrogens directly attached to that carbon. And I think that works. Let's see, there's 6 carbons. There's 3 oxygens, there's 2 OH groups, and there's 12 hydrogens. Is there 12 hydrogens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, boom! That is definitely a good one. I think I prefer that one there than my first structure. All right, guys. You don't need to get all of these right to get the A star, but as long as you can show you're working, you can smash it. Don't forget sharing's caring. Hit the like, punch up the bell, subscribe. I'll catch you lot on the next video.
You still here? It's over.